I don't think we need to spend much time here because we've actually already done some parametric equations, graphing of parametric equations. And I did that by plotting points, but I did it by way of showing you kind of how to check your work when you were eliminating the parameter. So let's pick an example, not example one in your textbook, because that's the same example as we did for the eliminating the parameter, where I ended up graphing it as well. Let's pick a different example. This looks like a pretty big leap, but remember we've already learned how to graph things like r equals 4 sine theta and r equals 2 cosine theta. So we're familiar with what it feels like to plug points or plug values in here and get an output value, and that's exactly what we're going to be doing here. One of the big differences is that we're going back to a Cartesian plane. I'm going to be creating a table of values, and for each value of t that I select, my functions are going to spit out an x value and a y value. The x value will come from this equation, the y value will come from this equation, and then the xy pair is what will get plotted. Because these are both trigonometric functions, I think it makes sense to, sorry, I'm grabbing the right tool here, to work with input values that are going to be easy to compute the sine of t. So I'm going to grab those common angles, those common input values. We'll start with those ones. Technically, these three are the only ones in quadrant 1, and these are quadrantal angles, but these kind of encompass quadrant 1, so we'll start with that. And notice that the sine of 0 is 0, so 4 times 0 is going to give me 0. That first x value is really easy to find. Cosine of 0 is 1, so this value right here, cosine t, is 1 when t equals 0, and so 2 times 1 is 2. That becomes my first y value. So my first point on the graph is 0, 2. It's right there. When t is pi over 6, I'm going to plug pi over 6 in here and here. The sine of pi over 6 is 1/2. 4 times 1/2 is 2. The cosine of pi over 2, or pi over 6 rather, is the square root of 3 over 2. That's a little messier. The square root of 3 over 2 times 2, though, that's just the square root of 3. So my next point is going to be 2 comma the square root of 3. So let's get an approximation for the square root of 3. I get 1.73205. There's no way I can graph that accurately, so I'm just going to write it as 1.73, and then the 3 tells me I don't need to round up. 1.7 is close enough. For pi over 4, when I plug pi over 4 in here, I get 1 over the square root of 2, or if you'd rather, you can think of that as the square root of 2 over 2. And I'm going to do that here because I have to multiply it by 4, and it's going to make it a lot easier. The sine of pi over 4 is the square root of 2 over 2. When you multiply that by 4, you get 2 times the square root of 2. 2 root 2. The cosine of pi over 4 is also the square root of 2 over 2. And when you multiply that by 2, you get just the square root of 2. So now I'm going to go get approximations for both of these. Normally when I do this, I just go grab all of my trigonometric values, and then I'll go back and get the approximation. So I think I'll do that with the rest of these. The sine, my next input value is pi over 3. The sine of pi over 3 is the square root of 3 over 2. When you multiply that by 4, you get 2 times the square root of 3. The cosine of pi over 3 is a half. A half times 2 is 1. And now I'm at pi over 2. The sine of pi over 2 is 1. Multiply that by 4, you get 4. The cosine of pi over 2 is 0. 2 times 0 is 0. So there are my first few points. Let me go grab, it looks like I only need one more approximation. I'll go grab that, and then when I come back, we can plot these values. Okay, so I have 0, 2 already. My next point is 2, 1.7. 2, not quite 2. So I'm there. My next point is 2.8, so almost 3, 1.4. Almost 3, about there, 1.4 is about there, so my point's going to be about here. My next point is 3.46, or about 3.5, comma 1, and that's there. Then I have 4, comma 0. Now, my graphing here is fairly inaccurate, right? I'm using a pretty fat pen, and I'm kind of having to guess at where, is that 2.8 or it's 2.8 maybe closer here, is 1.4 maybe a little higher, a little lower. So I'm kind of having to guess here. And that's the nature of the beast. I understand that. But also recognize that we started at t equals 0. So this is my first point. And my I'm working with parametric equations here. So I have to go in order. I have to start here, and I have to go in this direction. Now these are all the values that I got by plotting points starting with t values in quadrant 1, including the quadrantal angles, right? What I need to do now is pick some values from quadrant 2 and quadrant 3 and quadrant 4, and then find the x and y values that go with those as well. Now those are all going to be the same values, just potentially in a different order, and quite likely, at least half the time, they'll have different signs. Sometimes the x will be positive and the y will be negative. Sometimes the x will be negative and the y will be positive, and sometimes they'll both be negative. So let's go ahead and I'm going to erase this column, and I'll put in the values for quadrant 2, and I'll probably just erase all the values. And I am going to make a note that the square root of 3 is 1.7 and the square root of 2 is 1.4 and so on, because these values are going to come up over and over and over again. So I'll write those down somewhere else, probably up here, and I'll erase the rest of the table and we'll go into quadrant 2. All right, so here are my values that I wrote down, just as a reminder. That way I don't have to do the calculator every single time. Here are my quadrant 2 angles, and I'm also going to draw myself just a little quick and dirty 4-quadrant graph here, so I can talk about whether signs are positive or negative. All students take calculus. So our first t value in this second quadrant is 2 pi over 3. That is, we're in quadrant 2. That's this angle here. I'll just draw it in. I may have to redraw this this little sketch a couple times, but that's okay. Therefore, so this is my angle, 2 pi over 3, but my reference angle is this guy right here. So what is the sine of pi over 3? The answer is it's the square root of 3 over 2. So this value right here is the square root of 3 over 2, but is it positive or negative? It's in quadrant 2, sine is positive there, so it's positive. So this is the square root of 3 over 2, and we're going to multiply that by 4, which gives me 2 times the square root of 3. That means that the value for this one is 3.5. So 3.5 goes here for x. For y, I'm still at this angle. I'm still talking about this angle here. I'm still using the 2 pi over 3 angle with its pi over 3 reference angle. But now I'm going to take its cosine. Cosine of pi over 3 is a half. But cosine is negative in quadrant 2. So I have negative a half times 2 is negative 1. And that's my first point in this quadrant. Now, normally I would actually just do all 4 quadrants here. I'd do all my 0 to pi over 2 and then pi over 2 to pi. I would just do all the computations here. I'm doing it in quadrants for you primarily because I don't have a lot of room here, but also it gives us an opportunity to sort of break things down a little bit. I do want to make the point as I go that it looks like we're going to have to do all 4 quadrants because the points that we got from putting quadrant 1 values here all showed up in quadrant 1. And so our quadrant 2 values, I'm guessing, especially since we're dealing with a parametric equation here, parametric equations, is we're probably going to keep going. I'm not sure what's going to happen here. Actually, I am, but I'm not going to let on. We don't know what's going to happen yet, but we're going to keep going in this direction. So there's a very good chance that all of my quadrant 2 values will end up in quadrant 2. So let's keep going, and I'm going to speed things up just a little bit. Maybe I'll do one more, and then I'm just going to fill in the table because you know how to do this at this point. My next input value is 3 pi over 2, so I'm going to take the sine, sorry, that's 3 pi over 4. Take the sine of 3 pi over 4. Well, that's the same as the sine of pi over 4, and then the sine, S-I-G-N, may be positive or negative. So the sine of pi over 4, in fact, let me just do one more at reference angle here. I've got 3 pi over 4 here, And the reference angle is this angle right here. That's really hard to see. Let's do it this way. This is the reference angle. And that's pi over 4. So the sine of 3 pi over 4 is going to be numerically the same as the sine of pi over 4. That's the square root of 2 over 2. Square root of 2 over 2 times 4 is 2 times the square root of 2. So the value I'm going to get here is 2.8. And then I have to ask myself, is it positive or negative? Well, I'm in quadrant 2. That angle is in quadrant 2, and sine is positive in quadrant 2, so it stays positive. Same angle, 3 pi over 4, 3 pi over 4, cosine of 3 pi over 4 numerically is the same as the cosine of pi over 4. That is also the square root of 2 over 2. When you multiply that by 2, you get just the square root. So that's 1.4. 1.4. But I'm in quadrant 2, and cosine is negative there. So my answer here will be negative. All right, I'm just going to do these other ones. This one's going to have a reference angle of pi over 6. And this one's pi, so technically it has a reference angle of 0. So here are the values for quadrant 2. Here are the x coordinates, and here are the y coordinates. So let's plot those points now. 3.5, negative 1 is about here. 2.8, negative 1.4 is about negative 1.4. It's about here. 2, negative 1.7 is about here. And 0, negative 2 is here. So continuing the same direction, my curve looks something like this. In quadrant 3, we have, oh, I forgot to put my approximations in here. So square root of 3 is negative 1.7. Square root of 2, negative square root of 2 is negative 1.4. That's going to be enough. All right, so I have negative 2, negative 1.7, so that's about there. Oh, I forgot these other ones. 2 root 2 is 2.8, so this is going to be negative 2.8. 2 root 3 is 3.5, so this will be negative 3.5. So I have negative 2.8, negative 1.4, so that is about there. And negative 3.5, negative 1 is about there, and negative 1, 0. Oops, I forgot to multiply by 4. That should actually be negative 4, 0. I did my computation, but I forgot to multiply by 4. So my points in quadrant 3 give me that. And I can estimate what my points in quadrant 4 are likely to be, but I'm just going to go ahead and compute them anyway. We're in quadrant 4 now, so cosine is positive in quadrant 4. So the cosine function, the y function, is going to have positive values. And sine is negative here, so all our sine values are going to be negative, except for this one here. 0 is neither positive nor negative. Our points are negative 3.51, that's there. Negative 2.8, 1.4, which is about there. Negative 2, 1.7, which is about there. And then 0, 2 comes from 2 pi. Well, 2 pi is the same as 0, so I'm going to get the same output value when I plug in 2 pi as I did when I plugged in 0, and that is 0, 2, which is already on the graph. So I'll close the loop here. And that is the parametric equations for an ellipse with a major axis of 8 and a minor axis of 2. For those of you who are interested, you may want to recall that you can write the equation of this ellipse. It's centered at the origin, so it's not shifted at all. We have x squared over half the axis is 4, so that's going to be over 4 squared, which is 16, plus y squared over 2 squared, which is 4, equals 1. That's the rectangular or Cartesian version of the equation for the ellipse. Here is a version of a pair of parametric equations that give you the same ellipse. The difference is that with the parametric equations, I know where I started. And I also can tell which direction I went in. Now, I drew these arrows as we went along here. I wasn't saying anything about it at the time, but that is included in the information you have here. T is going to increase, right? We might start with t equals negative 10 and go to t equals 10. but we're going to start with the small value and go to the large value. In this case, we went from t equals 0 on our first chart all the way to t equals 2 pi. And that was because we chose common angle values to plug into our functions because both of them were trigonometric functions. I think it's really interesting to make the observation that this is very much like example 2 in your textbook in this section, but there are some differences. Instead of the x equation being 4 sine t and the y equation being 2 cosine t, they're reversed. The x equation is 2 cosine t and the y equation is 4 sine t. And the result of that is that, well, there are two differences. One is that the ellipse ends up being this shape. Let me see if I can draw it in here. It has a height of 4 and a width of 2 instead of the other way around. So the ellipse that we came up with in that example, we didn't do that together, but if you were reading the textbook, you would have noticed this ellipse. The other difference is that the motion is counterclockwise. And the one that we did, we went clockwise. The first point was here and the next point was here, and so we were traveling in this direction. With this example, we were traveling in this direction. And just to look, when t equals 0 in our equation was here. That was the first point we plotted. But in the example done in the textbook, the first point they plotted was here. So the starting point, the direction, and in fact, to a certain extent, the orientation of the graph can all be determined by parametric equations. And they're not the same as the, They're not the same as the Cartesian equation because the Cartesian equation just gives us the final result. We wouldn't know where we'd started or what direction we were going in. So you can make curves like this with parametric equations, which is really quite interesting. You can also make a lot fancier curves with parametric equations. We're going to be looking at that very soon. But that's the end of this video, and the next video, Applications of Parametric Equations, is the last one from the textbook. Now there are a couple of videos after this, but the last one from the textbook is 8.7 Applications of Parametric Equations. I'll see you over there.